Let's solve some problems involving joint probabilities. The first one we'll look at is a transportation network. There are 5 links or 5 roads between cities A and E, and we want to know the traveler will be able to successfully travel from A to E. There are 2 cases, one in which the 5 links are mutually independent, and the second case in which there is a degree of dependence between failure of links 1 and 2. So for such problems, it's a good idea to start by defining the relevant events. So here we have Fi, which is failure of link I going from 1 to 5, and the system failure, which we call Fab. Now, given the system logic, as you can see in the diagram, we can define Fab in terms of the element failures. We can also define the complement, the success event, Fab bar, in terms of the link successes. So the roads are open. The roads are open to travel. Let's look at Fab bar. For that to happen, link 1 must be good. The road must be open. Road 2 must be open, and between C and E, either 3 must be good, or 4 and 5 together must be good, or both. So that gives me the Fab bar expression that you see on your screen. In fact, we are going to use this Fab bar in solving the problem in both cases, because that is a little more convenient. Expressing the probability of Fab bar, we take advantage of the mutual independence. So the probabilities are multiplied with each other. So P of F1 bar is multiplied with P of F2 bar, and P of the bracketed term F3 bar union F4 bar intersection F5 bar. So let's expand the last term in terms of P of A union B. So that's PA plus PB minus PAB. And now we can use the independence of all the events, F1 bar, F2 bar up to F5 bar. Now, because we discussed this, if link failures are mutually independent, link successes are also mutually independent. So that would let us write the system success in terms of all the individual element success probabilities, and the answer for case A is given in terms of Q. Q is the link success probability, which is Q cubed times 1 plus Q minus Q squared. Now, when there is dependence between failures of 1 and 2, we need to be a little careful. So we can't write P of F1 bar F2 bar as the product of the two. For the second term on the right hand side, we can still do what we did before. But for the first term, P of F1 bar F2 bar, we need to consider the dependence that has been given. So how do we do that? P F1 bar F2 bar. So these two events are complementary, F1 bar F2 bar and F1 union F2. So we can write P F1 bar F2 bar in terms of P of F1, P of F2, and P of F1 F2. Now F1 F2, they are not independent anymore, so we can't multiply the probabilities. So we have to use the information given. So P of F1 F2 is P of F1 given F2 times P of F2, so it's 2P times P. So that gives me the probability of F1 bar F2 bar, that both are working, as 1 minus 2 PQ. And now I can go back to what I did before, and the success probability is now 1 minus 2 PQ times Q plus Q squared minus Q cubed. Now, which one is better? Which one, we'll use the word reliability a little later, but which situation is more reliable, or which success probability is a little higher? So we can just compare the two answers, and because 1 minus 2pq is always greater than q squared unless q is equal to 1, then case B has a higher success probability.